Several different sort orders. A clever extension of this idea was introduced in C-Store and adopted in commercial data warehouse, Vertica. So it started in C-Store and now it is being used currently with Vertica. Different queries benefit from different sort orders, so why not store the same data sorted in several different ways? Data needs to be replicated to multiple machines anyway, so that you don't lose data if one machine fails. You might as well store that redundant data sorted in different ways so that when you're processing a query, you can use that query that best fits the query pattern. Having multiple sort orders in a column-oriented store is a bit similar to having multiple secondary indexes in a row-oriented store, but the big difference is that row-oriented store keeps every row in one place in the heap file or clustered index, and secondary indexes just contain pointers to the matching rows. So here we're talking about replica. In secondary index, that's a heap file, right? A clustered index that points to matching rows. In a column store, there normally aren't any pointers to data elsewhere, only columns containing values. So there's no pointers containing to data or values somewhere, only columns that contain values. One query, three words. We'll use one identical query and see how it executes. First, B3 row stored, RDMS, second LSM3 firestore style, third bitmap index column store. Let me check, I think we have discussed, no, we haven't discussed it. So third bitmap index, which is the column store, the query, select asterisk from sales where product underscore sk in argument 30 comma 68 comma 69 next and store underscore sk equal to 3. Assume 1 billion rows. Product underscore sk has 100,000 distinct values. Store underscore sk has 1k distinct values. B3 Postgres / MySQL / traditional RDMS. Storage model row oriented. Data stored as tuples or index or non-immutable index. Index equals to non immute non-immutable list. So that's what tuples is. Index B3 mapping values to row IDs. Indexes are available. Create index IDX underscore product on sales argument product underscore SK. Next line, create index IDX underscore store on sales argument store underscore SK. So the B3 mapping, remember the B3 uh, uh, data structure of the B3. We have like a tree-like structure that mapping is value to row IDs. So how the query executes, step by step. First, use IDX underscore product, which find all row IDs where product underscore SK equal 30, then 68, then 69. Then union this row ID sets. Then third, for each candidate row ID, fetch the row, check store SK equal to 3, then fourth, return matching rows. I think we discussed this here. Let's see. Final mental declarative mathematical set base. Yeah. So this is the one we discussed earlier. So we're just gonna skip this. First, explain exactly what. There normally aren't any pointers to data elsewhere, only columns containing values means. Second, contrast it mechanically with row stores, heap plus B-tree. Third, tie it directly to bitmap indexes, LSM compaction, and everything we discussed. Fourth, explain why your brain flags this as new, even though it builds on old ideas. What does no pointers, only columns containing values actually mean? Let's strip this down to physical reality. Row-oriented database, Postgres or MySQL, physical layout, in heap file. We have row 1, row 2, row 3, row 4, B3 index on product underscore 80, SK, 30 to pointer to row 17, 30 to pointer to row 93, 69 to pointer to row 201. Key point index entries do not contain the data. They contain pointers, row IDs, page plus offset. So it doesn't have the actual value, just like the column to value. This is similar to how you would point it in a CPU architecture where you have a memory, base memory, and then you just need to have the offset. I mean, you don't have the actual value. You just know what register or what location in memory is that value. Then query execution equal follow pointers. This is why cache misses matter, rando IO matters. Pointer chasing cause CPU cycles. So because CPU needs to actually through that loop, this you need to cache the recently search once, and also that's the reason why the SDK in browser also matter, especially for Firestore, because they store cache as well there. Now column oriented store, C store slash vertical slash clickhouse, physical layout, column, column product underscore sk. Now I have 69, 69, 69, 74, 31, 31, 29, 30, 30, 31, 68, 69, then column for store underscore sk 33 3 3 5 3 1 1 3 3 3 1 3 3 Now the key sequence. There normally aren't any pointers to data elsewhere, only columns containing values. Means there's no heap file. There is no central row location. There is nothing to point to. So unlike B3, because the page are mapped to a value, here we have no central row location. There's nothing to point to. The column is the data. When you select rows, you really producing a bitmap, bit mask of positions, because the rows are related, with relates to the column position. I mean, they are entirely kind of like the column is the base. So in memory or with CPU architecture, the you get sometimes you get the location in the memory using the base plus offset. Here your base is the column. Why this is fundamentally different from secondary indexes? You already know this part, but the difference is subtle and deep. Secondary index in row store, index argument product underscore sk2 row id, then row underscore id to heap page, then heap page to row. Every query does indirection, pointer chasing, cache line jumps. So the cache line jumps kind of like the data bus in CPU architecture, the instruction and data bus. Multiple sort orders in column store. Vertica stores the entire dataset again, but sorted differently. For example, copy A sorted by product underscore sk colon, next line product underscore sk, uh, column, then next column store underscore sk, next column price, next column time. Then for copy B, sorted by store underscore sk, next line store, that's store underscore sk column, next column product underscore sk, next column price, next column time. Important, these are not indexes. These are full copies. Queries scan the best sorted copy. So as you can see, uh, we don't scan indexes. We scan the whole, or we copy the whole column. But again, it's more efficient if you sort that based on your workload. So you put that makes sense, the first one that makes sense to your workload. So when the text says a bit similar to having multiple secondary indexes, it immediately corrects itself. But the big difference is because index point, but sorted columns don't. How this connects to bitmap indexes? This is the missing bridge. You were confused earlier about why turn n distinct values into n bitmaps. Now it clicks. Bitmap indexes only work because columns are stored positionally. So that's the reason why you have n distinct map values into n bitmaps, because that value are the actual value of row from column. So column are stored positionally, row order is identical across columns. Bit k always refers to row k. So that row is actually the distinct value. There is no row pointer heap lookup in direction. Bitmap equal implicit addressing by position. That's why this works. Product underscore sk equal 31 and store underscore sk equal to 3. That's why you can interface to it using SQL, because bitmap underscore product underscore 31 um, and bitmap underscore store underscore 3, both bitmaps refer to the same row positions. This is impossible in a row store without pointers. So as you can see, this seemingly different number are actually uh, refers to the same row position. So they have different column, but they have same row position. This is impossible in a row stored without pointers, because you need to point this in other rows. But since we're optimizing for this CPU, we're just using the column as a base. We can definitely use that particular column because we know that they will be equal all the time, because we use that as an, we know that from this column, this is the value of its offset, because we're using like a CPU architecture concept. How this relates to LSM trees and why it feels familiar but wrong. LSM trees also say avoid random IO, write sequentially, use immutable segments. So your brain tries to unify them, but here's the crucial distinction. LSM trees are row-based, key addressed, keys to values, looks up by key, compaction merges versions. Column stores are position-based, scan address. It used the CPU concept of offset, because in CPU you can load in memory without knowing the actual location. You just to know to specify how far is that from that base position, in this case the column. Stores are position-based scan address. Values equals to position, not keys to values. So queries are set algebra, like and and or. Compression exploits repetition plus order. So since you know that position of the row in each base column, you could better compress it compared to um, row-oriented storage engine. Same physical instincts, different query philosophy. That's why it feels related but alien. Why this feels like a new concept? This is important. You accepted more layers, more complexity. Instead, column stores do something unsettling. They remove a layer entirely. No heap, no row pointers, no tuple identity. So we're not talking about the program here, uh, from the program counter having multiple abstraction. We're just talking about the actual layer of the CPU itself. So we don't actually have the transfer from memory to disk. That violates the Mendel model you built from OS3 easy pieces inside the machine, TCP or IP, relational algebra thought as logical rows. This is a representational shift, not a tactical detail. Your earlier stack was CPU to memory, to pointer to structure, to data. Column stores do CPU to array, to bitwise math, to result. That feels too simple, so your brain distrusts it. One visualization that usually makes it click. Forget databases, think spreadsheets. Sorry, let's go back to this. So we have CPU, then we have an input array, which has the same fixed rows. Then we do a bitwise math on it, and then result, kind of like loading it from the arithmetic logic store, and then storing or writing it from the to the back end, right? So that's the front end and back end. This is the front end of the CPU. This is the back end. The one that do bitwise math is the CPU. So that feels too simple. One visualization that usually makes it click. Forget databases, that's on user space. Think spreadsheet. Row store equal filing cabinet. Indexes tells you which folder. Folder tells you which paper. Paper has all fields. And then paper has all the fields, so you have like pointer chasing in b3 because the page reference to another until you get the actual value. In column store, x is equals to excel column. You highlight rows with a condition. So this is also kind of like a branch instruction where you could jump to a specific location in memory. You highlight rows with a condition. So if it meets the condition, you jump to that location. This is kind of like the same as that in CPU architecture. Then apply that highlight to other columns. So let's say you in other columns you also want this row. You highlight the like row 39, etc. No jumping, no fetching. So you don't need to reference it like a linked list tree or the B3. The B page we discussed in the previous video. No jumping, no fetching. Bitmap equal highlight mask. Bitmap is equals the highlight map mask. Final anchor, tie everything together. Here's the sentence that unifies everything you've been asking. Row stores locate data by identity, row IDs. Column stores locate data by position. Once you internalize identity versus positions, all of this snap into place. Bitmap indexes, no pointers, multiple sort orders, CPU friendly scans. Why Firestore can do this? First, forget sorting, copies, vertica. That's not the core idea. This is critical. Product underscore sk equal 31 and store underscore sk equal to 3 works even if the data is not sorted at all. Sorting helps performance. It is not what makes and possible. So this column storage still work without this sorting. It's just kind of like the optimization. It's not the base. This column storage still works, but if you want kind of like with relational database, it will work with just a table, but it will work better if you have like secondary indexes. It's kind of like the same with this. Sorting helps performance. It's not what makes it possible. The real reason and works is row identity is replaced by row position, index number. This is the missing sentence. Rebuild from something you already understand, your bash lsmdb. So from previous example, we have db underscore set key to value, append to log, then db underscore get key, scan log, take last value. This is key to value. We only scan the most recent version. Now imagine your database is not key to value but two columns. Like here, row 0, 1, 2, 3, product underscore sk, store underscore sk, important. Row number key is the only identity. There's no pointer, there's no tuple object. So there's no like further abstraction in user layer. We just know the offset from the base column. Color store physical layout. This is breakthrough. Instead of rows, data is stored like this. So in product underscore sk column, we have 69, 69, 69, 74, 31, 31, 29, 30, 30, 31, 68, 69. Then in store underscore sk column, we have 3, 3, 5, 3, 1, 1, 3, 3, 3, 1, 3, 3. Notice both columns have the same length. Index k in every column refers to the same logical row. So that's the key, they have the same length. This is the entire trick. Now, how product underscore sk equal 31 becomes a bitmap. So as you can see, before we mentioned that 69 and 3 has the same row. This is what it looks like. Now, how product underscore sk is equal to 31 becomes a bitmap. Scan the product underscore sk column. So let's see, product underscore sk equal 31 question mark. So this bitmap is the result of the predicate. No rows fetch, no objects created, just comparison to bits. So we just compare that k 30 equal to 31 with an offset of something like this, and then the bitmap is the result of the predicate. No rows fetch, no objects created, just comparisons to bits. Now do the same for store underscore xk equal to 3. So here we have index 0, 1, 2 and then value 3, 3. So this is where end happens, no magic. CPU instruction bitmap underscore product underscore 31 and bitmap underscore store underscore 3. So we have products and store, and then the result is this 0. Answer, no rows match both condition. If there were a row, both bits were 1, that row index is the result. So if there's a 1, that will be returned to the business analyst. But here, it didn't match. So in that product and store, that out of all like 100,000 product and 1,000 store, there's no result. But we can return that almost instantaneously to business analyst. Key insight: how did they become the same row? They never become the same row. They were aligned by position. Position is equal to row identity. That's why book says there normally aren't any pointers to data elsewhere, because the index number is the pointer. Where sorting and multiple copies actually matter. Now we add vertica strict. Without sorting, you must scan the entire column. Still fast, but on. With sorting, if data is sorted by product underscore sk, then product underscore sk equal 31 is a contiguous range. Bitmaps becomes a run 0000100. So compression is extreme. CPU can skip large chunk because since it's at the first sorted file, since you configure it or tailor it to your workload, it returns immediately that first available column. Now compare with your LSM example. This is the bridge. Your bash db grep key like code upper upper dollar key comma database. This is scan compare filter. Column store does the same thing, but LSM slash grep strings, column store integers. So for LSM or grep is still a string, and column store we're actually dealing with actual number. So that's a number being converted, or it's part of the instruction set of the CPU being converted from assembly to machine language. LSM graph, we have branches. In column store, it's vectorized. We determine it via position. LSM slash grep per row logic. Column store, bitwise logic. LSM slash grep row at a time. Column store, thousands at once. So you only search few rows at a time. In column store, thousands. Same idea, different execution model. What is a tuple here? In row stores, tuple is equal to physical thing, heap row. In column store, tuple is equal logical illusion. It is reconstructed only if needed, often never materialize at all. That's why analytics queries can return counts, sums, histograms without ever building rows. So it's the same with the CPU, right? It can immediately execute using ALU. You just know the base or what number you want to execute without ever building the rows. So a heap, it's a data structure, right? We discussed this heap row. So this is what the tuple is. Instruction by instruction, CPU view, simplified. For product underscore sk equal to 31 and store underscore sk equal to 3. First load compress bitmap for product underscore sk equal to 31. Second load compress bitmap for store underscore sk equal to 3. Third vectorize ends instruction SIMD. So kind of like with the CPU architecture, we will discuss this in the future video. With memory, you load A and you load B, and then you decode it and then execute and then write or store it back to the user. So fourth, count bits or iterate set bits. So this is you do that arithmetic or you count the bits that matches and then fetch only requested columns for these positions. No heap access, no pointers, no joins yet. Mapping this to Firestore plus your future analytics. Firestore row slash document oriented. Indexes to document IDs. Queries to pointer chasing. Cannot bitmap end efficiently. Great for OLTP, bad for analytics. Analytics side, big query slash ClickHouse. Column oriented, bitmaps plus scans. Perfect for OCR statistics, session analytics, AI feature aggregation, time series summaries. Real world architecture, what you're converging toward. Firestore users, you have sessions, permissions, metadata, LiveKit. For column store, we have events, OCR results, analytics, AI features. They are complements, not competitors. Final sentence to lock it in. Row store ask, where is this row? Column store ask, which position satisfy this condition? Once you hold into position instead of identity, everything you ask, bitmaps and compression, CPU usage becomes obvious.